Okay, welcome everyone to HAO Colloquium. Our today's speaker is Dong Lin. It is my great pleasure to introduce Dong Lin. Dr. Dong Lin is a project scientist from the High Altitude Observatory of NSF National Center for Atmospheric Research. Dr. Lin got his PhD degree in electrical engineering from Virginia Tech in 2019 before joining HAO as an ASP postdoc. He was promoted to Project Scientist 1 in January 2022. Dr. Lin is a member of the CGS modeling team and working group lead of precipitation and conductance. He has been primarily working on characterizing auroral precipitation and critical magnetosphere ionosphere coupling processes and effects during storm time. Today, Dong will be speaking on a story between Dragon King and Aurora in the world of MAGE. To Dong.
Thank you, Masumi, and thanks everyone for coming. And it's my pleasure to give a colloquium at my own institution. I just recall that last time when I gave a colloquium here at HAO was April 2022. So that has been like 2.5 years. I think that's kind of a normal frequency for like HAO employee and myself. And so as you know, I'm also a host myself for the summer colloquium series. And Nick and I had a conversation. So we're always a welcome volunteer. So it's part of the motivation for me to give this talk here. And also another thing to clarify that is that so my PhD degree is EE electrical engineering, and although I'm doing like a space science, sometimes people got confused. What is the relation between EE and the space science? But I think for many people here, it's not really that weird because back in Virginia Tech, we have many colleagues who are working on, for example, the silver down those infrastructures, and those are very powerful tools to study space science. Okay, so today I try to come up with a very creative title, so trying to bring more people, and looks like it's working. Glad to see everyone again. So I think among these few keywords, the Dragon King, Aurora, and the MAGE, people are probably most familiar with Aurora, kind of related to space science or heliophysics. And also, yeah, before I move on, let me just acknowledge all my collaborators as listed here from a number of institutions, and particularly my advisor when being here. Okay. So Aurora, I think people are probably not unfamiliar with Aurora, especially in recent years. So we have seen a lot of Aurora photos from social media. This is basically because we're entering the solar maximum of the cycle 25. This is just one of the articles I found online showing the splendid Aurora photos taken by people all over the world. And back in May and October, even here in Boulder at a relatively low latitude, we have also seen very nice Aurora photos. I will show one taken by myself in the next slide. But before this year, I think it's kind of a rare thing to see Aurora in locations such as Boulder. I remember before this year, the most famous photo was by Stan Solomon, our colleague. I remember there was a very nice plot by him, taken at the Mesa Lab. So it's great for us to see that Aurora, which is a representation of helioscience that is getting more and more attention or interest from the general public. That's kind of demonstrating the significance of our own research. I mean, as a heliophysics community, as an entity. So here, well, this is one photo I took on the page of my own home back in October. It's not as nice as what you just saw from online, but I really like this photo because for the past few years, I have been working on auroral precipitation myself, but this is really well, not really the first one because in May I also took one, but not as good look at this one. But this is really like in the first time in terms of this year that I directly saw the aurora myself. It's like I saw like a direct connection between my research. So well, you can see this red and the blue back in the cloudy sky. This is like 8 p.m. here in Boulder time. So what I have been working on, just like many of you, is not really that far away nowadays. It's a chance that we can see it in our real life. So again, this is just like by a part-time. I'm not even a part-time photographer, but just using my cell phone. So in real scientific studies, scientists can use more advanced cameras to take photos of aurora. For example, these are, and by the way, this kind of cameras are called imagers. And so on the left is a very famous image from the DMSP satellite using the SUSY imager. So this is basically a camera on board a satellite, and it's taking photos downward. And because of the limit of the field of view, so you can only see this one swamp during each orbit. And on the right-hand side, you kind of see this is like the collage of images from multiple images on the ground. So they are kind of looking up. This is ground observations, usually much cheaper than space-based. But I think the common thing between these two images is that you can see the aurora actually is featured by many different structures. So like here you can see this kind of arc, but also if you look more closely, you can see more small scale, like these tiny structures. So all of this just suggests that even though it's can be very beautiful in your cell phone photos, but to understand really what's going on is kind of not an easy thing, because just like shown by these images, really multiple scales and also very dynamically varying. And we know we don't see that every day. So when you can see it, it suggests something going on in the space. So just take one step further. So those images are essentially remote sensing, right? It's just taking photos or images. It's not really directly into the aurora. But nowadays in the space age, we can make use of, for example, satellites, which can really travel through the aurora region. So and we have also learned that aurora is basically caused by energetic particles from the space. They just ignite the topside atmosphere. So what are the distribution of those particles? And we can learn those information by making in situ measurements with particle detectors. So this is another two examples from the DMSP, just a different instrument called SSJ. It's basically a particle detector. And in these particle measurements, we are mostly interested in the energy distribution, because more energetic particles certainly can penetrate deeper. So we want to look at how many particles are at the different energy levels. So this is basically a distribution of the particle flux. So the amount of particles and with energy. So this is like 10th EV to 10th keV, and over time. And so what's interesting here is that this kind of energy time distribution, or in other words, the energy spectrum, shows quite different features in different orbits. Like this kind of structure is more like you see some concentrated distribution around a certain energy, right? So that suggests that so these particles probably have gone through the same acceleration, so that they got like the same energy gain. And so that's how this energetic name came along. There are other cases when you see like enhanced particle fluxes over a very broad range of energy. So here you can see a lot of particles at all this energy range from hundreds eV to tens keV. So this is another type of precipitation called broadband. And in the background, you see more like a greenish or diffusive. That's how they got the name diffuse precipitation. I think most of the time when you look at the night sky in Alaska, for example, when there's aurora going on, you would see like a very diffuse background. So, and for us, it's more important to understand like what are different physical mechanisms behind the different lookings of the precipitation spectrum. Making use of those in situ measurements over many decades. So earlier studies have surveyed the statistical properties of each type of auroral precipitation. Also, just to remind you again here, according to the language of the New World, there are these three types of aurora. Sorry, let me find my laser pointer visible. Do you see that? Still not? Okay. Anyway, just by looking at the spectrum of the aurora particles, we have came up with different types. And statistically, they also show very different distributions. For example, the diffuse electron precipitation, they tend to occur more on the night side and the morning side. So this is a map of the ionosphere when you look down from the top of the North Pole. So this is like the North Pole, and this is like the mid-noon, this is the midnight. So this is a polar view of the ionosphere. So you can see that the diffuse precipitations tend to have a preference on the morning side. But on the other hand, the monoenergetic, so again, they tend to get like the uniform acceleration. So this kind of precipitation tends to occur on the afternoon side. So this is like or dusk side. And the other type called broadband, they have a more preference over the midnight. So again, they are not, so this kind of categorization or terminology for different types of electron precipitation is not only determined by the spectrum feature. And when you look at the statistical distribution here, they do suggest the physical mechanism behind. And just as a introduction, we have learned that the diffuse precipitation is mainly caused by the wave particle interactions in the inner magnetosphere. And so those tends to like smoothly scatter those particles into the atmosphere. So that's why they tend to appear as more diffusive. While the monoenergetic is usually attributed to a quasi-electrostatic acceleration in the between the magnetosphere and ionosphere. So again, that's how they got the same energy gain. And the broadband is another type of accelerated. It's just different from quasi-electrostatic. They tend to have like a broader range. And all of these, both of these two accelerated, they are unified as discrete. So discrete and diffuse are the primary electron precipitation we have been talking about. So here is the full family tree of the precipitation we just mentioned, just to give you some more general background. I was mainly referring to electrons in the so far, but the ions, they can also precipitate. And there are different mechanisms for ions as well. And so for electrons, based on the physical mechanisms, there are diffuse, discrete. There's another type I didn't mention is the direct entry. So this is basically like when you consider the magnetosphere configuration, there's one special region when the electrons can directly enter, so basically that's in the Casper region, around the Casper region, when the electrons can directly enter the space environment. For diffuse, we mentioned the wave, plasma waves. There are different waves that can be responsible. And although like each type of wave has their own preference in terms of like occurrence. For ions, similarly, there are different mechanisms. So this just to give you a very general, broad idea. So in my study so far, I have been focusing on this diffuse and also and discrete for electron precipitation. So so when we talk about auroral precipitation, well, when we talk about precipitation, if you ask the people from other labs of NCAR, they would first think about the rain, right? Because rain is also precipitation. And so in our team, when we try to came up with a name for this model to describe precipitation, we thought about some culture background, and because a number of us are from China and other parts of Asia, and so we came up with this name Dragon King, which is a precipitation god in Asian cultures. And another feature of the Dragon King is that it has a number of offsprings, and so we just associate each of the dragon son or daughter to one of the physical mechanisms that we just talked about. So that's basically some culture background for the model name. Okay, before we move on, let's just also go over the motivation for doing all the precipitation or aurora study. So the aurora precipitation has a number of significances. So the first one is just from the origin in the magnetosphere. They basically means the charged particles from the magnetosphere get lost. So that's an important process to affect the status in the magnetosphere. And during the process, and they are mostly guided by the geomagnetic field. So, and when the charged particles move, that means a electric currents, right? And most of the time it's the electrons. So, so the field current itself is also an important aspect in our geospatial environment. And the third, probably most important, is that when these precipitation particles enter the topside atmosphere, they ionize the neutral background into plasma, so that they generate conductivity and conductance. So that in turn regulates the electrodynamic coupling between the ionosphere, thermosphere, and the magnetosphere, and let alone the changes to chemistry and other energy budget. So these are like a quick summary of the significance for all the precipitation studies. So the tools I've been using, like I mentioned in the introduction, so it is a so-called MAGE model, multi-scale atmosphere geospatial environment. I guess most of the people are familiar with this model, but here just to show the diagram for the current iteration. It consists of the magnetosphere, ideal MST, and Gamera model, and also a ring current model. This is because ideal MST is not a good assumption for the inner zone, where the charge separation and kinetic effects become more important. And also we have this TGCN model from NCAR, from HAO, for the topside ionosphere, and all of these are two-way coupled. So this is a fundamental tool, the MAGE model that I've been using to study the auroral precipitation. So a little bit more on each type of the precipitation. Just to recall the primary types we mentioned earlier, the diffuse electron precipitation statistically contributes the most to the energy budget and the number flux in terms of the total electron precipitation. So to calculate the diffuse electron precipitation, which is physically attributed to the wave particle interactions in the magnetosphere. So we are relying mostly on the inner magnetosphere module of the MAGE, which is RCM. So RCM solves for the convection drift of electron ions, and more specifically, we want to know how different plasma waves contribute to the electron loss. So far, we have considered Carl's wave and the Heath waves. Those are the two primary waves causing the electron precipitation in the magnetosphere. And this method was originally reported by Margaret Chen, but we were able to implement that and have a lot of upgrades in MAGE. The second type is called monoenergetic. So this one physically different. So it's attributed to the acceleration between the ionosphere and the magnetosphere. So basically, we need to get like how much acceleration is needed. So we are using the classic theory initially proposed by Friedman and Lamel. Basically, it's assuming like when there's a lot of electron precipitation, which means there's upward field line current, we solve for the relationship between the currents and how much thermal flux is available, and using the relation, we can derive the monoenergetic electron precipitation. Yes.
So I always thought the fact that we can do mapping from magnetosphere to high latitude ionosphere is because it's equal potential, near equal potential. So that's why you can use the potential from magnetosphere to do that. But it sounds like there is a drop. There is a potential drop that particles.
Right.
So maybe my original understanding was totally wrong.
Yeah, I think you're certainly right. So I think what we're doing now is we still assume it's equipotential between the ionosphere and the thermosphere, especially when we do the mapping of the ionosphere convection back to the magnetosphere. That's still true. But I think here, I think it's like an approximation. And also, you think about the distribution of the amount of precipitation. If you look at the global map, it's not like everywhere you have this potential drop. So it's kind of like an approximation. But I think more strictly speaking, if we want to take into account, because right now when we solve for the amount of potential drop, is assumed to be somewhere between the ionosphere and the inner boundary of the magnetosphere. So that's kind of the gap region. You may just add in or subtract the potential drop when you map the ionospheric potential back. But that's kind of a very dirty way because we're not really dealing with the processes in between. So that's why we still keep the simple assumption of equipotential when we do like a convection mapping.
And in the region where there is a drop, usually how big is the?
So for Mount usually it's a few kV. Yeah, and yeah, seldom goes above like 10 kV. So yeah, and right, so that's the typical values. Okay, the last type of primary precipitation or the broadband is due to, well, physically they are attributed to kinetic Alpha waves. Again, it's assumed to occur in the gap region. So we just, but we know statistically this wave precipitation or broadband precipitation is related to the, well, physically they are related to kinetic Alpha waves, and statistically we know the kinetic Alpha waves are related to the arsenic Poynting flux. So like when there's Alpha waves launched in the magnetosphere, they propagate along phase lines, and then they cascade down to small scale so that they can more efficiently interact with the electrons. So we are not resolving the kinetic processes in the gap region. We just make use of the statistical relation between the arsenic Poynting flux and the broadband electron precipitation flux. So basically, this is how we do the modeling here. We sample the E field and the B field, and we calculate the Poynting flux by filtering out the non-arsenic component. And then, based on the arsenic Poynting flux in the phase line direction, we make use of some empirical relation to get the so-called BB or broadband electron precipitation flux. So this is like a semi-empirical way to deal with the third type of electron precipitation. Okay, so here is a little more illustration of how the precipitation model works. Also starting with inner magnetosphere diffuse. So this is like a snapshot in the inner magnetosphere, and this is like the map of the wave model we mentioned. So yeah, as you can see, inside the plasma pores, this is like a dark blue. There's like a heat wave being responsible for the electron precipitation, and outside the plasma pores, shown by this white curve, is when the Carl's wave responsible for the electron precipitation. And because of the empirical wave models are determined by the available data from satellites, so we haven't got a good coverage of this very far away region. So in those regions, we just assume it's like a strong diffusion, kind of the simplest assumption. And so this kind of this empirical model tells us like the lifetime of the electron in the inner magnetosphere. So here, like this dark region means their lifetime are shorter, or in other words, the electrons in this place are more easily lost. And on the right is just the energy flux of the electron precipitation based on such a method. And this is from the inner magnetosphere perspective. And so the reason that we want to consider different plasma wave, like a heat wave or Carl's wave, is just because if you look at like observational data, that's just indeed the case. In the inner magnetosphere, the source region of the most diffuse electron precipitation, that's just how they are distributed. So this is like one orbit from the Valence probe. As you can see, so this yellow curve is the orbit of the Valence probe. So as you can see, when it travels through inside the plasma sphere, and it crossed the plasma pores, and then encounter, this is a plasmaspheric plume, and then back to the plasma sphere again in this one orbit. You do see that there are different waves occurring in there. So that's why, and also they are contributing to the electron precipitation. So that's why we need such a physical model to better understand like the different processes responsible for the electron precipitation. So here is like a full picture of the Aurora map and its origin. I use a quote because it's just based on what we have implemented so far. There are still other mechanisms we haven't implemented yet. So what's shown here? So this is a field line current in the ionosphere. This is the monodiffuse electron precipitation energy flux. And if we do a mapping along the field lines to the magnetosphere, so this is like in the equatorial plane. For example, on this Aurora map, you can see such a arc structure on the dusk side. So again, this is a polar view of the ionosphere. You have such an arc on the dusk side, and that maps to partly to the like this location in the equatorial plane on the night side, -15 RE. And if you compare this location with the magnetic field, you can see that it's kind of like near the boundary of the plasma sheet here. So this is like the BZ profile in the equatorial plane. And so this just shows like, and also if you look closely here, you can see some flow channel structures. So this higher, this red structure means it's like a flow channel approaching the Earth. So, okay, yeah. So this is like one of those typical Aurora arc structure you would see with images. And here's like the connection I just mentioned. And because this is like near the open closed field line boundary, so not all of them can map to the equatorial plane. So at this very high latitude, some of them are open field lines, so they wouldn't get to the equatorial plane. And another structure on the night side, here you can also see this very intense aurora, and they correspond to the upward field line current, like this blue region. It has to do with another flow channel here on the post-midnight sector here. So what is shown here is that using the physics-based model of Dragon King in MAGE, we can track like how each aurora form is produced in their source region in the magnetosphere. Similarly, in this flow channel breaking zone, we also got a lot of organic Pauling flux that's supposed to be responsible for the broadband electron precipitation. But I'm still working on like what's the relation between this broadband and the mono structure we just mentioned. That's still ongoing work. A quick milestone is that so this model, the Dragon King, has been as part of the MAGE has been released to CCMC. So it's available for runs on request. And so this is part of the CGS team efforts. Yeah, we're very glad to have Dragon King playing some role in there, making contributions. And this is a link for the MAGE run on CCMC. If you haven't got it, it's a good time to give it a try. So next I'm going to talk about a few applications using the MAGE model, well, certainly including the Dragon King. I will mainly cover these three aspects. The first is about some of the mesoscale structures in Aurora and typical MI coupling processes. And okay, so I actually talk about the SAPs in previous talks. So I want to just very quickly mention that. So SAPs means subaurora polarization streams. So it's one of the most common structures in the ionosphere. So if you look at the convection pattern, it's often a very narrow flow channel on the dusk side. So what's shown in this study is that we found in order to resolve a very narrow structure like a SAPS, a few degrees in latitude, it's very important that we got the diffuse and mono precipitation separately. And this one cannot be achieved by simply increasing the resolution. Instead, you need to introduce this different physics behind the mono and the diffuse precipitation in order to capture such a SAP structure. And this is essentially determined by the physical mechanism that generates the SAPs, which has to do with the relative location between the field line current and the Aurora boundary. Okay, so here's a cartoon plot. I hope that helps. So basically, if you look at the magnetosphere, we have this is like the inner boundary of the electron precipitation, and the green is like the inner boundary of the field line current. So basically, in order to resolve a SAPs, you have to get these two. You have to resolve the gap between these two boundaries. And again, they are determined by the different physics behind. And you cannot simply increase resolution without dealing with both physical processes. And recently, and after that, we also made more progress in terms of the mesoscale MI coupling. So we were able to resolve both, explain both SAPs and a new phenomenon called dawn side SAPs. So the typical SAPs usually occur on the afternoon side, but in recent years, there was a report of a new phenomenon that the SAPs can also be, the sunward flow can also be observed on the morning side. And we used this MAGE model to explain the generation processes for the dawn side SAPs, and it was attributed to the very strong driving conditions, usually during the main phase of a strong storm. So, so again, this demonstrates the powerful capability of this MAGE model in resolving such a typical mesoscale structures. DAPS is another well-known mesoscale structure in the ionosphere. So here I'm citing another example from teammate of the CGS modeling team. So Korean has been using the model to explain how another type of aurora is generated. It's called a giant annihilation. Basically, sometimes if you look at the aurora image, you can see such like a wave structure here. This is again the DMSP SUSY data, and they have like a wave-like structures on the Aurora boundary. And this is explained with the MAGE model and attributed to the interchange instability on the inner boundary of the plasma pores. So basically, if you map the Aurora form along phase lines to the magnetosphere, so if you can trace the magnetospheric origin, you can get here on the plasma pores, due to the gradient in the velocity and the density, it is kind of a unstable situation. That's how it generates the undulations in the aurora in the ionosphere. So again, this kind of study just requires you to resolve the processes in both the ionosphere and the magnetosphere. So next, I'm switching to another aspect. So how we can use this MAGE model to understand some of like a space weather effect. So here's one example from the so-called SpaceX storm. So this before the main storm this year, the SpaceX one was probably the most well-known space weather event in recent years. So what we did is to trying to understand the neutral density variation during this event. This is like from February 1st to the 7th. And here you can see the black curve is the swarm satellite data suggesting like the neutral density at that satellite orbit altitude had a relative variation of about 100%. So basically, the neutral density almost doubled during this time, and it's right after the SpaceX corporation launched a number of Starlink satellites into space. So that's why people connect. And sorry, it happened to be a moderate geomagnetic storm going on, and when the SpaceX lost like 40 satellites, that's how people associate these two facts together and trying to think about any space weather hazards. And as swarm data suggested, like almost double the neutral density, which is a critical factor in satellite loss. So we try to understand like how much like the storm effects is contributing. So we use the MAGE model, and we were able to quantitatively reproduce the density variation during such a storm event. You can see the purple curve from the MAGE results is nicely reproducing the density variation suggested by swarm data. But as a comparison, which is like the common case in the industry, people just use relatively simple empirical model like the MST to estimate such storm time variation, and they tend to very underestimate the density variation. And so this is attributed to that such empirical models, they don't really resolve the storm processes. So that's no wonder they couldn't get the energy variation and so on during the storm. So which also demonstrates the advantage of a physics-based model like MAGE in space weather studies, such as neutral density prediction on such a time scale. So this is a quick animation showing the simulated density variation over that event. So we also compared the MAGE model to standalone TIGCM. So the difference is that the MAGE basically treats the magnetosphere as a dynamic input, while in standalone TIGCM, we only rely on empirical models such as Weimar or Hillis to represent the high latitude forcing. So because like a Weimar or Hillis, these empirical models are based on statistical data, so they tend to like smooth out. So that's why on timescales of such a storm event, they tend to underestimate or miss those dramatic changes. So this is like the iron drift measured by DMSP satellites, which is an indication of the convection E field or potential. So you can see that major results is resembling the actual case data better than the empirical or standalone runs. The third aspect is about the thermodynamic coupling. So we have talked about the particle precipitation and also the electrodynamic coupling. but there's another channel between the magnetosphere and the ionosphere, which is treated as thermodynamic. Let me see. Okay. So in the magnetosphere, there are different populations. Some of them are highly energetic, like the so-called ring current or even radiation belt. But there's also a general cool background called the plasma sphere. And when they overlap with each other, they tend to have like coulomb collisions. And that's one way to generate heat conduction. And those heat conduction can be transported along field lines down to the ionosphere. So you may expect some thermal effects due to such a thermodynamic coupling. So here is a valence probe measurements of the inner magnetosphere, where you can see this is the energetic protons and oxygen ions. This is like the electron distribution. So you can see some overlap in this region, and we can calculate the heat flux. So this kind of heat flux is making a difference in the IT system. We also make use of the semi model, which is an inner magnetosphere model, to get like a global distribution of the heat flux, and we use that to drive the TIDCM and try to understand what are the thermal effects in addition to the particle and the electrodynamic coupling we mentioned earlier. So this is a controlled experiment using TIDCM with and without the heat flux from the inner magnetosphere. So here you can see this is the electron temperature, electron density, and the red line emission rate. This is a global map of geographic latitude and the solar local time. So you can see that so this is the net effect, the difference between the two runs. So when we include the heat flux, you can see a substantial electron heating in this region. So this green curve is like the Aurora boundary. If you pick one point and then look at the vertical distribution, you can see that using the heat flux, they can generate like more than 500 Kelvin enhancement in the electron temperature. And similarly, consequently, there's like a reduction in the electron density. And we combine all those parameters like temperature, density, and the neutral background. You can estimate the red line emission. They also produce a big difference in the red line emissions. So this just to demonstrate like how the heat flux can make a difference in the IT system, in addition to the particles and the electrodynamics. We also learned that in addition to the heat flux, another process which we just talked about, the SAPs or subaurora convection, they can also change the energy budget in the ionosphere. So we want to compare like how does the thermodynamic coupling and the electrodynamic coupling matters in terms of the IT response. So we did another controlled experiment. This is like the net effects of SAPs in terms of the electron temperature and density. So basically, with the SAPs, with the enhanced subaurora convection, we can also get enhancement in electron temperature and more substantial changes in electron density. And consequently, they also change the red line emission. So here is a polar view, probably more helpful to explain the difference. So remember in the earlier slides, I showed a photo of the aurora, right? We see red aurora, sometimes green, but red is the most common one because they come from the atomic oxygen at the relatively high latitude. But the thing about what causes those red emissions. And so this study is to explain the relative contributions from like the heat flux and the convection. So the heat flux, they can contribute to enhance the red emission in the dusk side and the midnight, while the SAPs, the plasma convection mechanism, they also contribute, although in a broader region in the ionosphere. So with this controlled experiment, we provide a direct comparison of like different physical mechanisms in affecting the red line emissions. So this a more side-by-side comparison. So both the thermal effects and the plasma convection, they can change the red line emissions, but they change them in a very different way. The heat flux mainly affects the location where it input to the ionosphere. So it's concentrated near the subaurora. But the plasma convection or SAPS mechanism is affecting a much broader region. Well, this is basically because they can change the ion clearance with the neutral background. So I'm not going into too many details here, but the key point is that there are multiple ways in the space system that can change the visible light.
Can I ask you a question about blocker? You mentioned that was subaurora, but it looks to me over on the dust side, you're up around 70 degrees or higher. So is the conditioning of the system such that the inner magnetospheres come up to those latitudes, or what do you mean by subaurora?
Well, I think it's kind of like a roughly speaking. If you look at the green curve here, can you see the green curve? Not a two. Okay, so this green curve is the Aurora boundary. The green curve is the Aurora boundary. We use a number flux threshold of 10 to the 6 per square centimeter per second. So you can see most of the red line enhancement is in this subaurora region. Although there's some of them actually go into the Aurora region, but most of that is in the subaurora. That's just because the heat flux is produced in that area, and it's very localized. I think that's a key point. The heat flux effect is very localized because they only change the electron, and they have very minimal effects or negligible effects on other, like the ions in the ionosphere. But the SAPS mechanism is different because SAPS is plasma convection.
Sure.
Yeah, so they have
Yeah.
I think that's the most important conclusion from this comparison. Okay, thank you. Okay, so let's talk about some of the future work. So I think regarding the precipitation, one of the most important direction, in my opinion, is to get the full spectrum. So traditionally, we just assume the precipitation particles as a Maxwellian distribution, but in reality, that's not always the case. Actually, most of the time, not the case. And the spectrum shape actually matters in terms of the IT response. So this is like a early work by Fong. They have shown that how different energy levels can affect the ionization rate at the different altitudes. So now with the Dragon Key model, we are able to resolve a full spectrum of those precipitating electrons. So we can further explore like how different mechanisms is generating a different spectral shape, and how does that generate a different conductivity profile, and how does that feedback to the IT system. Another factor is that the IT system, the neutral background in the thermosphere also matters. So in the studies of atmospheric conductance or conductivity, many of the times people use incoherent scattering radar measurements as ground truth, but as far as I know, they also have to rely on certain assumptions of the background, especially the thermosphere neutral density. People may use MCs, for example, widely used, but that could be another source of uncertainty, like discussed by this Kepler study. Using a different profile, you can get very different Hall to Peterson conduction ratios. And as we covered earlier, especially during storm time, the neutral density can actually go very substantial variations that tend to be underestimated by the empirical models. So this is another direction I'm trying to explore. supported by my early career proposal, how does the storm time neutral variation affects the conductivity effects. When we talk about precipitation, the most important application is certainly in conductance and conductivity. And here we also, I'm also exploring how kinetic effects such as the electric jet turbulence can make a difference in terms of the IT-MI coupling. So this is one experiment with the MAGE model by comparing with and without the ET effects with the kinetic scale in the ionosphere, how that can change the convection E field so as to the entire system. One last update is that so I have been collaborating with MAGE from NASA GSFC using the same model. So this independently from the CGS team, other folks have been able to derive like heat flux using the MAGE model sets. So and based on our prior work, we should be able to explore those heat flux effects in a more self-consistent way. So we were just doing like a one-way experiments in the study just reported. So this is another direction to go. Okay, to summarize, so in MAGE, we have been using the Dragon King model to characterize different types of aurora precipitation based on their physical driving mechanisms. And this model together has been able to support all kinds of studies in geospace storms, such as mesoscale structures, like aurora forms, subaurora convections, SR arcs, and space weather effects, and so on. And also just want to advertise again, the MAGE model is available on CCMC for run on request. Okay, here is like highlight thought of the work that I have been doing. So aurora precipitation stands for a particle coupling or mass coupling between the IT system and the outer space. We consider like the convection E field or this like a Poynting flux that represents a electromagnetic pathway between the topside atmosphere and the outer space. And the heat flux is suggesting a third way, I call it a heat or thermodynamic coupling. So these are like a grand picture of the studies of I have worked on different coupling pathways between the topside atmosphere and the outer space. So I just found it's a very fascinating picture. Lastly, just show what does it mean by the word of MAGE. So in MAGE, we have been using different logos for different model components. For example, Gamera is like a turtle, Dragon King, and Voltron, Hydra, and all of those. So this is just like a artistic representation of all those fancy tools we have been using. So let me stop here and take any questions. Thank you.
So, what is missing to make MAGE 1.0 at CCMC? Right now you have it at 0.75.
Yeah.
What is the piece that will make it 1.0?
I think that's the TCM coupling when being, or I'm not sure if Mike is online, but yeah, I think I can announce that we are planning to make that released in March.
So what is the current ionospheric? So is it a mix? And you still have the field line currents that are dependent. I mean the conductivity is dependent on the field line currents.
Yes.
And so forth. In the current 0.75 model or no?
So the top side want to be so basically like a MAGE 1.0 is like this. So it has all the magnetosphere, inner magnetosphere, and the TCM, and it will be released to CCMC planned to be in March.
Okay.
And it has all those methods I just mentioned. There will be also upgrades for certain parts, like the RCN will be replaced by Ryger, registry is like the next generation of RCM, like a Gamera.
But back to the ionosphere piece, so TIGCM is not currently in the CCMC. Really?
No, only standalone TIGCM, but in 1.0, it will be included.
Thank you.
About the photon precipitation, you mentioned at the end, I think if I understood, you do plan to include,
Yes.
because it can be an important source of ionization in the subaurora region, like in the SAPS region, which affect the conductances there.
Yes. Yeah. So what I'm showing here, this is a plot provided by our colleague Anthony Sosella from APL. So he has been working on proton precipitation driven by emic waves. And let's go back to very early. So if you look at here, actually ion precipitation can have different origins. Another important mechanism is called phelan curvature scattering. So I have been working on that part. So yeah, both of us are working on this part, and it's going on.
Ling?
Is there any?
Yes, so my question is also about like ion precipitation. But Don already said it will consider the including the proton precipitation. But Don, is other than proton, is there other ion like O+ precipitation as well?
I wouldn't say no, but quantitatively this should be very small. I mean, in terms of the amount compared to like protons. So I'm not
Mostly proton.
Yeah, mostly proton. Yes.
Okay.
Yeah.
Is there any latitudinal boundaries for each type of precipitation? Means for if it is diffuse, then it's restricted to that dash latitudinal region. If it is mono, it only there for the high latitude or the low latitude as well. Means is there any latitudinal boundary like what you show as a MLT there here?
Latitude boundary. So usually, if you look at mono, because that's attributed is caused by the acceleration in the upward phelan current. So upward phelan current and mostly on the dusk side, right? So they tend to occur at a relatively high latitude around the open-close boundary. But we don't use like any predefined boundary. But yeah, they do have some preference.
Ling, go ahead.
Oh,
please.
yeah. Okay. Yeah, I have follow-up question on the ion precipitation. So, in order to consider ion precipitation, what do you do? The two parts. One is in your Dragon King part. Is it currently already including ion precipitation, or not?
It's not officially included. We are still working on some of the testing, and I would say I still need some more work on that. It has not been the focus, but it's always on the plan. And since we have seen increase in interest in ion precipitation, so we want to give that a higher priority in the next.
Okay.
It's not officially in the released version yet.
Okay, and then on the other part is in the like TIGCM, Aurora ionization. So currently it's electron ionization. So in order to when you have ion precipitation, then you need to add that part to the Aurora ionization code as well. So you need to update the TIGCM as well, right?
Yeah. I think now there's already a function in there using one of the France paper, 2013 or so. Yeah, it's similar to the electron procedure using the energy and to get the ionization rate.
Oh, you mean it's already included in the TIGCM Aurora ionization code?
Yeah, in TIGCM, there's already a function to calculate like when you have ion precipitation, how much ionization rate is producing. We are just not using that yet.
Oh, okay. Is that a proton or ion, including all ion?
It's just for proton.
Proton. Okay.
Yeah.
Thanks.
Thank you.
So in all our current like Weimar, they don't include heat flux, right?
As far as I know, Weimar Hills, they don't. In TDCM, there is a very simple background uniform.
So does it change during storm time?
No,
No.
that's Wenbin's paper, 2006.
Okay, so that's why I was wondering if you include this kind of, the highlight here, what you showed, the heat flux, how much of a difference of thermosphere temperature do you expect?
Yeah, so this is like a direct. Well, you were mentioning thermosphere. I think for thermosphere probably the neutral is probably not too much. In this study, I did look at both neutral and plasma temperature. The heat flux is mainly affecting the electron and also very locally. And I didn't see a very substantial difference in ion temperature or neutral temperature. So yeah, that's what I have found so far.
I also have a question about the heat. I usually think of the magnetosphere as being collisions in the sense that the meet-free path is much larger than any characteristic scales in the magnetosphere. And when you talk about Coulomb collisions, producing this heat flux, is that happening in the ionosphere thermosphere, or are you talking about Coulomb collisions in the magnetosphere?
Yes, it is. The magnetosphere is also very large. So here is mainly in the inner magnetosphere near the plasma pores.
I can see that in the plasma sphere itself, that could be true. It's because the plasma sphere is much denser than the magnetosphere, typically by 2-3 orders of magnitude.
Right.
I'm just confused at that plot that you showed where you have heat flux coming in at 70 degrees latitude. That's got to be far away from the plasma sphere.
No, that's indeed the plasma pores. It's near the plasma pores.
At 70 degrees latitude.
Right. That's geographic. That's geographic.
Oh, that was geographic.
Yeah. I think I mentioned this geographic. I did this.
No. Go to the polar plot where you showed the effect of the heat flux compared to SATs. Yeah.
This one?
No, back.
This one?
There. Yeah.
Yeah, this is geographic.
Oh, that's geographic.
Yeah.
Okay. Well, that explains. Okay. Thank you.
Sorry. Yeah, this is why I showed this green. Well, maybe I should use a different color for the Aurora boundary, but you can see it's not centered around
Yeah.
the pole.
Yeah. No. Okay. Fine.
So, yeah. And also because the plasma pores is where the hot population from ring current and the cold population from plasma sphere, the overlap. That's why it's usually concentrated near that region. And that plasma pores region happen to be like the near the Aurora boundary. So that's why it's usually in the sub-Aurora.
Any other question from anyone?
Me.
Yeah, so Don, in the last slides, you show the coupling, MIT coupling in the form of electromagnetic and the mass and the heat. So I noticed that for the electromagnetic, it's like both way, and the mass is also both way, and the heat seems to be just one way. Is the heat also both way?
Oh, thank you. This is really a great question. So the reason, so first let me explain the two-way. EM coupling is two-way. I think that's understandable. We have both waves coming down and the E field mapping, right? And the particle have coupling has two-way as well. We have a particle coming down, but it's also like an outflow. Even though I have done very limited work on outflow. For the heating, I think mainly it's because of temperature difference. So in the plasma sphere, the coolest space in the magnetosphere, they are still like a 1 eV, right? So 1 eV is like 11,000 K. So that's still much hotter compared to the atmosphere. But I think I should add another two-way arrow for heat, because 2 weeks ago in the CGS workshop, I learned from some other people there may be heat flux from the low atmosphere upward. So maybe there's should be a converging two-way arrows for this heat channel. But I'm not sure. I'm not an expert in that regard.
Yeah, because I thought that like a day and a night is different. Like a night, daytime it's like going up maybe, and the night time is coming down. not quite sure. And also another question is this the size of this arrow is not to the proportion of the magnitude of the
No, it's very random. It just depend on like this logos I made to illustrate that. So yeah, this didn't mean to be scientific significant. Yeah.
Mhm.
Question? I have a very stupid question.
Oh,
Because I'm not in this subject. You had that electron density and heat flux anti-correlated.
yeah.
What's the reason of that?
You mean why here we have a depletion where
Yes,
the temperature is enhanced
side.
previous?
Where which side I forgot. Yes, this one.
This one?
No.
Oh, this one?
Yes.
Oh, okay. So you mean why here a stronger flux has lower density? Oh, okay. So this is basically so this is from Valence probe orbit. So this one is crossing so this high electron density means it's inside of the plasma sphere. So inside plasma sphere is closer to the Earth, they have higher electron density. But these energetic ions, the ring current, they cannot get into that far. So that's why in very inner side of the plasma sphere, we don't have as many energetic or hot ion populations. And right, so when the exits the plasma pores in the plasma sheet or ring current region, the plasma pore has like a very sharp gradient. The electron density drops very low, but that's where you have more like energetic ions. So basically that's the boundary of the plasma pores.
Thank you.
Yeah, I may should have shown like a global map. I think this one later. Yeah, something like this one. Yeah. Thank you.
Thank you.
In that electrojet turbulence, you are incorporating that electrojet turbulence through this model, but most of the aspect of these models are MHD based. So I'm not clear how the kinetic electrojet turbulence effects are you incorporating with this.
Oh, this is implemented from the TCM side, ionosphere side. So this is attributed to the kinetic effects in the IT system.
Okay.
It's based on some prior work by Jin Liu and also Mike, who women is familiar with those. So they have been working on like how so the general background is that when there's a very strong E field, they tend to trigger the kinetic effects that further enhances like the nonlinear currents or electron temperature, so they would modify the conductivity. So that's implemented in the TCM side. Yeah.
The parameter is model.
Uh,
As a parameterization of kinetic.
yeah.
Not a kinetic.
No, we don't solve for kinetic directly. Too much if we do everything.
Okay.
Thanks everybody.
Thanks, Dong.
Yeah.
Very nice talk.
Okay, thank you.